basically we are directly discussing this heat exchanger. Previously we have discussed the subjects, right, by starting with concepts, but here I am directly going to heat exchanger by assuming that you have basic knowledge about this heat transfer, right, the conduction, convection, radiation and all. So basically what is a heat exchanger, right? So heat exchanger is a device. It is going to facilitate the heat exchange between two fluids, right, which are at different temperatures. So heat exchanger is basically a device, right, that facilitates the exchange of heat between two fluids that are at different temperatures without mixing them. So there are, if we assume that there is a solid surface, right, which is separating this fluid 1 and fluid 2, right, this must be some solid surface, right. So in heat exchanger or in double pipe heat exchanger, generally the construction is like this only, right. In double we will see, right, here you are having that inner diameter and here outer diameter, and here you will have your fluid 1, here you will have your fluid 2, right. And fluid 2 will be again enclosed by some what we can say the material which will not allow heat transfer, right. So this is how you are having your construction. So this is particular some solid which is separating this fluid 1 and fluid 2. So whenever we are discussing about heat exchanger, what will happen is convection will happen, right, or convection will take place in both the fluid, right, here and here, while in the solid we will have some conduction, right. So this is basic of this heat exchanger. So that is why whenever we are discussing heat transfer in heat exchanger, it is better to consider overall heat transfer coefficient. Overall heat transfer coefficient. Right, let us say it as U, right. So once we have this basic idea, then here rate of this heat transfer at a different location will be different in an heat exchanger, right. So suppose we will see this how actually different heat exchangers are like, right. But suppose if you discuss about some basic what you can say your basic construction of this heat exchanger, then suppose you are having here your cold fluid in and cold fluid out, while here you are having your this hot fluid in and hot fluid out, right. Here let us say cold fluid, here let us say hot fluid, right. So here you may have TC in. If we are assuming that parallel flow, then you will have here TH inlet and TC inlet, while here TC outlet and TH outlet. We will see what is parallel flow and counter flow, and this is shell and tube type heat exchanger. This also we will see, but for now you can consider this simple heat exchanger. So in this what happens is the heat or sorry not heat, the temperature difference will be different at different point of means at different point in this heat exchanger, right. it is not same at all points. So what we are doing is we are taking this mean temperature difference, right, and in that not arithmetic mean, generally logarithmic mean temperature difference is considered. Logarithmic mean temperature difference is considered in heat exchanger, right, which is known as this LMTD, right. So this is how you are having some basic idea about heat exchanger and heat transfer in this heat exchangers, right. So yeah, as we have come to know in the introduction that in heat exchanger we will use this overall heat transfer coefficient, and we will consider this logarithmic mean temperature difference, right. So now if we first go through various types of heat exchanger, then here as we have discussed this shell and tube type heat exchanger, right. So in this this is parallel flow. When this cold fluid and hot fluid are having the same inlet, I mean inlet not at different place, they are flowing parallelly in the heat exchanger, then it is considered as parallel flow. Means inlet of hot and cold fluid both are on the same side of the heat exchanger, so that is why it is known as this parallel flow. While in counter flow, the cold fluid will be entered at the outlet of this hot fluid. So this is how you are having parallel flow and counter flow, and this is how temperature is going to vary in parallel flow and counter flow. So as you can see, the obvious advantage of counter flow is so here as you can see, the obvious advantage of counter flow is the this hot fluid is having less temperature at outlet than the cold fluid, right, while it is not so in case of this particular parallel flow, right. So this is how you are having means a higher temperature drop of hot fluid, right, in comparison to this parallel flow. So this is how you are having parallel flow and counter flow heat exchanger. Here this is a gas to liquid compact heat exchanger for a resident air conditioning system. So here basically when that space is not enough, in that case you are having these fins, right, in your compact heat exchangers, right. So you must have seen this in that two-wheelers cylinder which is having fin, right. So our lungs are also heat exchanger, right. It is also a compact heat exchanger in which some this kind of fins and all are there. So this is how, where that area or space is not available at that time, how much heat is transferred per meter cube or per volume is important. So at that time this kind of compact heat exchangers are used, right. So apart from parallel flow and counter flow, you are having this cross flow heat exchanger also, as it is mentioned here, right. And this again this shell and tube type heat exchanger is also there. This is a double pipe heat exchanger maybe, right, and this is the shell and tube type, right. So this is how you are having, actually this is based on the direction of fluid, right, or hot and cold fluid, while this is based on the construction. This is also shell and tube type only, right. So these are the various types of heat exchanger, right. Once you have idea about these various types of heat exchanger, then we can go for calculation of this what we have discussed, that overall heat transfer coefficient. So if we take this double pipe heat exchanger as it is mentioned here, you are having cold fluid here in annular space, and here you are having this hot fluid. This is again some insulating material, right. So this is how you are having your heat exchanger, right. So as we have discussed here on both the fluid side you will have convection, right? Convective resistance is mentioned as this 1 upon Hi and 1 upon H naught A naught, while R wall for this conduction, as you must have idea about this, that is given by ln d naught by di upon 2 pi kl, right? So this is how you are having your R total in case of this heat exchanger or double pipe heat exchanger will be Ri plus R1 plus R naught, right, or Ro for outside if you are considering it. So if we further simplify this, then we can write this R total as 1 upon Hi plus ln d naught by di upon 2 pi kl plus 1 upon H naught A naught, right? So once you have idea about this resistance, then we can also represent the heat transfer as this overall heat transfer coefficient plus area and the temperature difference, right? So this basically heat transfer will be seen at both inlet and outlet areas, right, of that double pipe. So Ui Ei delta T can be equated to U naught A naught delta T, right? So once you have idea about this, then what you can do, this is overall heat transfer coefficient, as we have already discussed, right? It is generally given in watt per meter square degrees centigrade, and it is identical to this heat transfer coefficient H. Now as you know, this Q or this heat transfer can also be represented with this temperature difference upon the resistance, right? And as you know, this particular delta T by R is nothing but this 1 upon UA, right? So once you write it in this term, then this 1 upon UAS can be represented as 1 upon UEI or UIAI upon 1 upon U naught A naught, right? So if you equate this delta T by R, which is this again heat transfer, to this UA delta T, then you will find that your R is this 1 upon UAS, right? Now as you know, R we have already defined with this, right, 1 upon HIAI plus this ln d naught by di upon 2 pi kl plus 1 upon H naught A naught, right? So what you can do is you can equate this to directly this 1 upon UIAI and 1 upon U naught A naught, right, which is nothing but this 1 upon UAS only. So if we assume that this particular thickness of this solid pipe, as it is mentioned here, right, this particular thickness is very small and this conduction through this wall is negligible. So if we consider this as 0 or almost 0, then our this R total will be Ri plus Ro, which is nothing but 1 upon HII plus 1 upon H naught A naught. Now this 1 upon HIAI and 1 upon H naught N naught will be directly then equated to this, and further if we assume that AI is almost equal to A naught, which is the total that surface area, then you can even simplify this 1 upon U is equal to 1 upon HI. Let me write it more clearly. So this 1 upon U can be represented as 1 upon HI plus 1 upon H naught. Now once you have this relation, then what is going to happen to your overall heat transfer coefficient is, if HI or H naught is going to be greater than 1. If hi is greater than h naught, or let us say h naught is greater than hi, then that particular term 1 upon hi in this case will be almost equal to 0, or 1 upon h naught in this case will be almost equal to 0, right? So what is going to happen is this overall heat transfer coefficient will be almost near to any of this, right? In this particular case the overall heat transfer coefficient will be near to this, and here it will be near to this. Now when this kind of situation arises, when you are having this gas liquid heat exchangers, in that case this kind of situation arises because gases are having less heat transfer coefficient in comparison to liquid. So we will see all this when we will discuss numericals, right? So for now you can have this idea that how this overall heat transfer coefficient can be represented. Now apart from this, if you go for one more important characteristic of heat exchanger is or one more thing we need to consider while looking at the heat transfer in this heat exchanger is this fouling factor. So what is this fouling factor? Fouling factor is deterioration in the heat transfer rate, right, or heat transfer rate. Why? Because over the period of time there must be some accumulation of deposits takes place on the walls of heat exchanger, right? So which will provide some additional resistance, right? So because of that you are having your decreased heat transfer coefficient or decreased overall heat transfer coefficient, so your resistance is going to increase and performance of heat exchanger will degrade because of this, right? Now what are the different what we can say factor which can result in this increase in this resistance is this precipitation of solid deposit, precipitation of solid deposits on the heat exchanger's wall, or corrosion of those heat exchanger walls. It is because of this chemical fouling, right? Or you can also consider the growth of algae on this heat exchanger wall, right, which is nothing but biological fouling. Right, so this is how various reasons due to which there is increase in resistance and it is going to degrade the performance of this heat exchanger. So once you consider this fouling factor, then your total resistance will have some added factors like this fouling factor at inlet, right? So it is going to increase as we have discussed. This will remain as it is, right? This RF output and this 1.10. So this is how you are having consideration of this fouling factor, right? So once you have idea about this, then we can go to this analysis of heat exchanger. So before going to this graphs, first let us see what is this analysis of heat exchanger. So generally two methods are used for analysis of heat exchanger, that is lmtd and effectiveness and NTU method, right? These two methods are generally used for analyzing heat exchanger. Now what are the different conditions in which we are applying these two different methods? So when heat exchanger you are designing a heat exchanger to achieve a specified temperature change, right, in a fluid stream, right? And you know the mass flow rate. So at that time lmtd is applied, right? So in order to achieve a specified temperature change, right, in order to achieve a specified temperature change in a fluid stream, right, so at that time what the mass flow rate will be known, right, with known mass flow rate. At that time this lmtd is going to be applied, right? While when NTU method is going to be applied, so when you need to predict the outlet temperature, right, of hot and cold fluid, right, in a specific heat exchanger, so at that time this effectiveness and NTU method is going to be applied, right? So in order to predict the outlet temperature of hot and cold fluid, right, so at that time you are using this effective NTU method, right? So we will see both of this method one by one, but before going to discuss this both the method, we first have to have idea about some basic terms and basic phenomena occurring in heat exchanger. So if we consider the heat transfer in this heat exchanger, then if we consider that heat added to this cold fluid, then it will be given by this mc delta T, right? This will be the heat transfer to the fluid, right? So here this mc is mass flow rate of cold fluid, this cp is specific heat of this cold fluid. Generally it may happen that specific heat varies with temperature, but here it is within this temperature is not that much deviating or not in that range where it is going to affect this specific heat. So we are considering constant specific heat, right? And this Tc out and Tc in is inlet and outlet temperature of cold fluid. So whatever amount of this heat is going to be transferred to cold fluid, that must be rejected by this hot fluid, right? So here inlet temperature of hot fluid will be higher, right? So here it will be Th in minus Th out, right? So this is how we are having this heat transfer in cold fluid and hot fluid in heat exchanger. Now what we can do is, in order to simplify this, we can define one more term as heat capacity rate. Heat capacity rate, right? So for hot fluid and cold fluid, we have defined this heat capacity rate as m into c, right? Cph, right? Here it is mc, right? So this is basically the capacity of cold fluid and hot fluid, right, to carry heat and to reject the heat. So this is how you are having this particular heat capacity rate Ch and Cc. So if you see this particular figure here, in this figure, what you can see is there is a constant temperature difference throughout, right? So what it depicts is, here your Cc is equal to Ch, then only this temperature difference can remain same throughout, right? Because what we have seen just now is the Cc into delta T in cold fluid is equal to Ch into delta T in hot fluid, right? This is what we have seen, right? Here Cc is mc Cpc, Ch is mc Cph, right? So if temperature differences remained or maintained same throughout, it simply means that Cc is equal to Ch, right? While in case of some specific heat exchanger like boilers and condenser, what happens is there is a phase change, right? So when phase change takes place, at that time the delta T is 0, right, in that case, right? So what happens is heat capacity in that case goes to infinity, right? So here actually if you see, in case of this condensing fluid, your this hot fluid is remains at same temperature, so for them this heat capacity is going to infinity, right, because its temperature is not going to vary, right? So similarly for boiling, what is going to happen is the hot fluid is going to reject the heat, but cold fluid is going to remain at same temperature. So in that case the Cc is going to be infinity, as you can see here, right? So basically what happens in this particular case of boiling or condensing is the heat transfer in that case is given by that mass flow rate of that phase changing fluid into the enthalpy of that phase change. So this is how heat transfer is going to be calculated in that case, right? So this is how you have to have idea about this boilers and condenser, in which you are having this one of the fluid is having infinite heat capacity, right? So after having this basic idea about this heat exchanger, then we can go to this LMTD, right, which means this logarithmic mean temperature difference. So in this, as you can see in this figure, if we focus on a particular portion of the heat exchanger, then in that particular portion we can consider how this heat transfer is taking place. So if you consider that small portion, so in that portion, let us say this heat transfer is this minus mh cph dth, right? So here this minus is as this heat is removed from hot fluid, so that is why this minus sign is considered here, right? Similarly, if you write it for cold fluid, then it will be mccpc dtc, right? So from both this equation you can write that dth is equal to minus delta q upon mhcph. Similarly dtc can be written as plus delta q, upon mccpc, right? So from this you can write this dth minus dtc is equal to, let us say, dth minus tc, right? And if you take this minus delta q common, then you can write as 1 upon mhcph plus 1 upon mccpc, right? Now heat transfer can also be expressed in terms of that overall heat transfer coefficient and that area, right? So heat transfer can also be,
Sir,
yes,
can you explain that above expression again?
yeah. So here what we did is simply we have written this heat transfer in that particular area which we have seen in this figure here, right? This particular area we are considering how heat transfer is taking place between hot fluid and cold fluid. So for that, what is going to happen is this hot fluid is going to reject the heat and cold fluid is going to get the heat. So as we are considering in thermodynamics, whenever heat is leaving the system, we are going to consider it as negative, and whenever it is going to be added in the system, it will be positive, right? So by considering that, we are having this delta q for hot fluid and cold fluid, mc delta t only, right? and then we have rearranged this in form of dth and dtc, and then we have taken the difference between them, right? Okay.
Sir, dTH corresponds to change in hot fluid.
Yeah, temperature of hot fluid.
Then how D comes out of that bracket?
See, it is differentiation, right, of this difference between hot fluid and cold fluid's temperature. So dTH minus dTC I have combined as the differentiation of that difference of that particular temperature, right? Okay.
Means it is at particular position.
Yeah, it is a particular position, right?
Okay.
Okay. So once you have idea about this, then as we know, heat transfer can also be represented as this delta Q is equal to U Th minus Tc for that particular small area ds. It can also be represented as this, right? Now if you put value of this delta Q into this above equation, then what you are going to get is this dTh minus Tc upon Th minus Tc is equal to minus UdAs, right, upon this whatever this MHCpH and MCCpC, right? So this is how you are having this equation. So once you got this relation, then you can integrate it from inlet to outlet, right? So once you integrate it from inlet to outlet, then you can get this equation that ln Th out minus Tc out on Th in minus Tc in, right, will be equal to this area will be now full area VAS, right, on 1 on MHCpH plus 1 MCCpC, right? So this is how you are having your relation. Now further you can simplify this equation, because you know we have seen that this heat transfer in cold fluid and hot fluid are represented by this, right, Tc out minus Tc in, right, and this MHCpH Th in minus Th out, right? As we know this, what you can do is you can put the values of this MCCpC and MHCpH in above equation. So if you do that and simplify, then you will finally come to a simplified answer of this, as this heat transfer is nothing but this UAS delta Tm, where this delta Tm is logarithmic mean temperature difference lmtd, and this delta Tm is given by this delta T1 minus delta T2 upon ln delta T1 divided by delta T2, right? So this delta T1 is temperature difference at inlet, right, while this delta T2 is temperature difference at outlet. So this is how you are having the heat transfer in your heat exchangers, right? So once you have idea about this LMTD, then we can go for that effectiveness NTU method also, right? So let us now go for that effectiveness NTU method. So in this effectiveness NTU method, first we have idea about what is effectiveness. So as you know, in this case you need to predict those output temperatures and all, right? So you are not having those output temperatures and all with you, right? So let us see first what is effectiveness, right? Effectiveness in this heat exchanger is given by actual heat transfer rate divided by maximum possible heat transfer rate. Right, which is equal to this Q by Q max, right? So as we know already, Q we have already defined as this, right? Tc out minus Tc in equal to this Ch Th in minus Th out. Right, we know already how this actual heat transfer rate in this heat exchanger. Now what we need to define is what is this maximum possible heat transfer rate. So maximum possible heat transfer rate will come from this delta T maximum. You have to have idea about this delta T maximum. So where is delta T maximum? So if you consider that Th in minus Tc in, then that will be the maximum temperature difference in heat exchanger, right? So for maximum heat transfer rate, you have to consider this delta T max. So this Q max is equal to this C mean into delta T max. Now C mean may be CH or CC, you need to check, right? So as we have defined here delta H max from this Th in minus Tc in, and this will be available from mass flow rate of hot and cold fluid. So once you have mass flow rate of hot and cold fluid and inlet temperatures of hot and cold fluid, then you can calculate the Q max, right? So, and if you have idea about the effectiveness of heat exchanger, then you can easily calculate the actual heat transfer coefficient, actual heat transfer from this simple relation, right? So if you have effectiveness of heat exchanger with you and inlet temperatures of hot and cold fluid, and mass flow rate of hot and cold fluid with you, then you can calculate actual heat transfer rate, right? So this is how you are having this effectiveness of your heat exchanger, right? So apart from this, what you are interested in is let us see how you can calculate the effectiveness for parallel flow heat exchanger, right? So if we can calculate the effectiveness in parallel flow heat exchanger, right? But before that, we will go to that equation which we have derived here, right? In this lmtd we have derived this one, right? This one, this relation, right? So this equation you can simplify to this, what I am going to write here. So that equation can be written as this ln Th out minus Tc out upon Th in minus Tc in is equal to minus Cas upon Cc 1 plus Cc by Ch, right? That MC, CPC and CPH is considered as the CC and CH respectively, right? So now once you have this, and we also have this Q is equal to CC and TC out minus TC in is equal to CH TH in minus TH out. So from this you can actually write this TH out from this side, which is nothing but this TH in minus CC by CH TC out minus TC in. So once you have this TH out from this relation, you can put this value into this equation, right? This above equation. This can be put in this equation, right? And at the same time you are going to add and subtract TC in. So if we put the value of TH out in the above equation and we add and subtract TC in, then what we will have will be something like this: TH in minus TC in plus TC in minus TC out minus CC by CH TC out minus TC in divided by here it is CH, right? Let me write it clear. The CC by CH. Yeah, so here this TH in minus TC in will remain as it is and equal to minus UAS by CC 1 plus CC by CH. Now if you can further simplify this equation, right, then how can you write this equation will be this ln 1 minus 1 plus CC by CH TC out minus TC in upon TH in minus TC in, right, equals to minus UAS by CC and plus CC by CH. Right, now as you know that effectiveness is nothing but Q by Q max, right? So this CC TC out minus TC in upon C minimum TH in minus TC in, right? So from this, if you can make this TC out minus TC in upon TH in minus TC in as subject, then you will have this effectiveness into C min by CC. So this is what you are going to put into this equation, right? This effectiveness into C min by CC. So you can plug this into the above equation. So when you will do that, you will be able to write your effectiveness in parallel flow as 1 minus exponential of this minus UAS upon CC 1 plus CC by CH, right, divided by 1 plus CC by CH C min by CC. This is how you can represent the effectiveness of parallel flow. Now in order to reduce the complexity, dimensionless parameters they have defined dimensionless parameters as number of transfer units, right, NTU. So NTU they have defined as not minus, actually you can directly write US upon C minimum as NTU. Similarly, capacity ratio is also defined as this C, only C, right? CC is anyway in cold fluid, so this capacity ratio is C itself, which is represented this C mean upon C max. So if you put this dimensionless number into the above equation, then you can finally write the effectiveness in parallel flow heat exchanger as 1 minus exponential minus NTU 1 plus C, right, divided by 1 plus C. So this is how you can have this effectiveness in your parallel flow heat exchanger. Similarly, if you can calculate all these things for counter flow, then you will get something like this: 1 minus exponential minus NTU 1 minus C minus here 1 minus C exponential minus NTU 1 minus C. Now some special case as we have discussed, like boiler or condenser, in which the C will be equal to 0 because your C max will be infinite. C max is a heat capacity, and heat capacity is infinite in case of boiler or condenser, right? So for that the C will be 0. So if you put the C will be 0, then what will happen? This maximum effectiveness will be there, which is given by this 1 minus exponential of this minus NTU, right? You need to have, so basically this one will be effectiveness or maximum effectiveness, right? And effectiveness will be lowest when the C will be 1, then E will be lowest, right? So this is how you are having this effectiveness NTU method. This effectiveness actually as mentioned here. Similarly, you can write this NTU for parallel flow and counter flow, and for C is equal to 0 also, right? You can convert those equations in terms of this NTU also instead of effectiveness. So if you convert them, then this NTU for parallel flow can be written as 1 minus E 1 plus C, right? Similarly, NTU for this counter flow, C minus 1 right? And for C is equal to 0, this NTU can be written as minus ln 1 minus E. So from this effective NTU method you can have these relations, right? So once you have idea about all this heat transfer in heat exchangers, and how you can calculate LMTD, and how you are having this effectiveness of heat exchanger, what is NTU in heat exchanger, then you can go for solving some of the questions from GATE, right? So let us see. It was asked in GATE 2003, in a counter flow heat exchanger for the hot fluid, the heat capacity is 2 kJ per kg Kelvin, mass flow rate is 5 kg per second, inlet temperature is 150 degrees centigrade, outlet temperature is 100 degrees centigrade. Then for cold fluid, heat capacity is 4 kJ per kg and mass flow rate is 10 kg per second, inlet temperature is 20 degrees centigrade. Then neglecting heat transfer to the surrounding, the outlet temperature of the cold fluid in degrees centigrade. Can you calculate this?
Yes, sir.
So please try and tell me what are you getting. So here what are the data given is this specific heat of hot fluid is given as 2000 joule per kgK, right? Similarly for cold fluid is 4000 joule per g Kelvin. Then mass flow rate of hot and cold fluid is also given, right? For hot
B, sir.
sorry
B.
B, yeah. So anyone else have got the same answer? It is 5 kg per second and 10 kg per second, right?
Yes, yeah.
Okay, so TCI is given as 20 degree centigrade. TCO you need to calculate, right? So THI and HO is given, right? THI is 150 degree centigrade, THO is 100 degree centigrade. So once you have all this data, you can simply equate the heat transfer in hot fluid and cold fluid, right? That is nothing but mc delta T for hot fluid and cold fluid, right? mc Tc of minus Tc in ln Hcph Th minus Th. So mc is 10, right? cpc is 4000, then tc out you have to calculate, right? Minus 20. mh is given as 5, here it is 2000, right? And here it is 150 minus 100, right? This is how it is. Yes or no? Correct?
Yes, sir.
So if you solve this, then you will get 32.5, right? So which is given as your this answer B. Okay, now if you go to the next one, then in a condenser water enters 30 degrees centigrade, sorry, and flows at the rate 1500 kg per hour. The condensing steam is at a temperature of 120 degrees centigrade and cooling water leaves the condenser at 80 degrees centigrade. Then specific heat of water is 4.187 kilojoule per kgK. If the overall heat transfer coefficient is this watt per meter square Kelvin, then the heat transfer area is, can you try this one? Hello.
Yes, sir.
Yeah, so please calculate. So it is a condenser, right? So what is going to happen in a condenser? Steam is going to be converted to water, right? So you will have steam, right, and this water temperature is going to increase, right? So what is given is water enters at 30 degree, right, and water leaves at 80 degree, and this steam is at 120 degree centigrade, right? It will remain same as it is mentioned, right? So you can first calculate the LMTD, right? What will be the LMTD for this case? Delta Tm is delta T1 minus delta T2 upon ln delta T1 by delta T2. So what is this? Here 90 minus 40, right? Ln 9 by 4. So what is this delta Tm?
61.66.
Yeah, it is almost 61.66, right? So once you have this, then you can consider any one fluid's heat transfer, right? Here you can consider heat transfer in water, right? So for that, first you need to calculate the mass flow rate of this water cooled fluid. What is mass flow rate? 1500 kg per hour. So what will be per second?
0.41.
0.4167, yeah, kg per second. So once you have this mass flow rate and this CPC is given 4.187, delta T you know, right, for water, that is 80 minus 30. So once you know how heat has transferred in this
Is the
cold,
answer A?
sorry,
Is the answer A?
yes, so let us see how you will get that. So we know that heat transfer is this MCCPC TC out minus TC in. Right, this is heat transfer in cold fluid, which is equated to the heat transferred in this heat exchanger, right? This UA delta Tm. So MC you have calculated as 0.4167. CPC you know 4.187. Then T out minus T in you know 50. Here it is kilojoule, right? So we need to multiply it with 1000 also. 4.187 into 1000. Right. This can be equated to this UA delta Tm. U is 2000. A you need to calculate. Delta Tm you have calculated as almost 61.66. So from this you can write area. So what is this? Hello.
0.71707.
0.707 meters square, right? So your answer will be here 0.707. Now if we go to the next one, then here hot oil is cooled from 80 to 50 degrees centigrade in an oil cooler which uses air as the coolant. Now the air temperature rises from 30 degree to 50 degrees centigrade. The designer uses a LMTD value of 26 degrees centigrade. The type of heat exchanger is. Can you try this question? So here you need to actually calculate the LMTD for both the case, counter flow and parallel flow. So hot oil is cooled from 80 to 50 degree. Yes, let us say 80 to 50 degree. Now what happens is this temperature rises from 30 to 40 degree. Let us see. So this is your parallel flow, right? And what what is going to happen in counter flow. This will be 80 to 50 and this will be 30 to 40, right? To 50, right? It will be counter flow. Because here it is inlet temperature, right, for both, while here it is TCI and here it is THI, right? This THI and TCI. So this TH out, TC out. Similarly here TH out, here TC out. So are you getting this? How we have come up to this? Is it clear to everyone?
Yes,
Yes.
sir.
So once you have this clear idea, then you can calculate that delta T1 at inlet and delta T2 at outlet in both the case, and you can calculate that delta Tm for parallel flow and delta Tm for counter flow. Right, you know delta Tm is delta T1 minus delta T2 upon ln delta T1 by T2, right? You know.
26.85.
Sir, it is neither of parallel and across.
Sir, so D, sir.
Yeah, so the answer will be D cross flow, because what is going to happen is in parallel flow you will have, tell me what you are getting in parallel flow.
28.8.
Sorry,
24.85.
it is 24.85 in parallel flow, and in counter flow
28.8.
in counter flow it is 28.85, right? So this delta Tm is neither of these two, so that is why we can go with this cross flow. Okay.
Sir, what is double pipe?
Pipe.
Sorry,
Double pipe.
double pipe is actually what we can say, arrangement of heat exchanger, as we have seen earlier, right? Here double pipe is simply misleading, because
Like pass wala.
yeah, here we have seen, right, in this case this is double pipe, right?
Means it may be parallel, it may be counter.
So that option is misleading, right? You need not to consider that option, right? Okay.
Okay.
Yes.
Yeah. So let us go to the next one. Here in a counter flow heat exchanger, hot fluid enters at 60 degree and cold fluid leaves at 30 degree. Mass flow rate of hot fluid is 1 kg per second, and that of the cold fluid is 2 kg per second. The specific heat of hot fluid is 10 kilojoule per kgK, and that of the cold fluid is 5 kilojoule per kgK. The log mean temperature difference for heat exchanger. I guess you can calculate this. Yeah. Hello.
Yes, sir.
Yeah. So please go ahead and calculate.
Is it 30?
Yes, correct. So how will you get this 30 is, you have again you need to again equate this heat gain by cold fluid is equal to heat rejected by this hot fluid. Now in counter flow, as you know, here you will have TH in, TH out. Similarly here you will have TC in, TC out. So MC is given as 2, CPC is given as 5 kilojoule per kgK, TC out. TC out is mentioned as 30, right? Fluid leaves at 30, right? Cold fluid leaves at 30. So TC out is mentioned as 30. TC in is not mentioned. MH is given as 1 and the CPH is given as 10 to 10 raised to 3. Then again hot fluid enters at 60 degree and TH out is not with us, right? So if you rearrange this, then here it will be cancelled, right? 2 into 5 10 this all will be cancelled anyway. So what you will get is TH out minus TC in is equal to 30 degree, right? So here actually both are same, right? At entrance and at exit delta T is same, so in that case delta Tm or this lmtd is equal to the delta T1 or equal to delta T2, which is nothing but 30. Okay, yes,
And one doubt,
yes,
sir. In this case, the
yes,
T in minus TC out
yeah.
is it equal to change in hot fluid, or is it equal to cold fluid temperature?
I didn't get, what are you telling?
Means here whatever LMTD is getting,
Hmm.
so is it equal to change in either hot fluid temperature or change in cold fluid temperature?
Actually, it is this mean temperature difference throughout this heat exchanger, this delta T, right? Are you getting what we are discussing about this delta T is?
Yes, but is it equal to hot fluid temperatures change or cold fluid temperatures change?
It is equal to the temperature difference at inlet or temperature difference at outlet. Okay, because it is same.
Matlab,
Temperature difference at inlet and temperature difference at outlet is same. It does not necessarily mean that this TH out minus or TH in minus TH out is equal to this TC in TC out minus TC in.
मतलब ऐसा हो भी सकता है या नहीं भी?
I guess it will automatically occur here because then only it is true, right? So that is also true. The same is drop in that what you can say temperature in hot fluid as it is gained by cold fluid. Yeah, you are telling that only, right?
But is it always true?
Yeah, then only you will have this, right? I guess. Yes or no? Basically, this is this straight line, right?
Yes, sir. In this case, heat capacity ratio for hot and cold fluids are same. That's why it
Yeah,
is the
yeah,
slow
yeah.
heat line.
This whatever we have defined, right? This C, that CC upon CH is equal to 1. In that case, this particular thing will take place, right? Both heat capacity is same. Okay, are you getting?
Means it is always true.
I guess yes, but still I will check, right? I will check that then.
Okay, sir.
Okay. So the next is the LMTD of a counterflow heat exchanger is 20 degree centigrade. The cold fluid enters at 20 degree and hot fluid enters at 100 degree. Mass flow rate of cold fluid is twice that of the hot fluid. The specific heat at constant pressure of the hot fluid is twice as that of the cold fluid. The exit temperature of the cold fluid. You can try this one, right? Yes or no?
Yes, sir.
Hmm. you are having this counter flow, right? So for hot fluid and cool fluid you will have like this. You are having 100 degree to this TH out. Here there is TC out, right? And here it will be 20 degree centigrade, right? So from this, if you go with that same heat transfer in hot fluid and cold fluid, then here what is mentioned is mass flow rate of cold fluid is twice, right, that to that of that hot fluid, and specific heat at constant pressure of hot fluid is twice as that of cold fluid. So if you put both this condition, then this MCCPC will be equal to MHCPH, right? So basically again you will have this TC out minus TC in is equal to TH in minus TH out. Yes or no?
Yes, sir.
So this will again give you that T H in minus TC out is equal to TC in minus TH out. Correct? Sorry, TH out minus TC in. Right. Correct. So here your LMTD is again. So LMTD is again delta T1 equal to delta T2, right? Equal to this any of the difference. Yes or no? So this delta T1 is delta T1 minus delta T2 upon ln delta T1 by delta T2. Right, so if you consider this delta T1 by delta T2 as x, right, then what is going to happen is this delta Tm is equal to limit this x tends to 1, you will have here this delta T2 x minus 1 upon this ln x. So if you apply that L'Hospital rule, then you will have this delta Tm is equal to delta T1 is equal to delta T2, as we know, right?
Is the answer 80, sir?
Sorry?
Is the answer 80 degrees Celsius?
Yeah, it is 80 degrees centigrade. So from this only you can have this answer, right? Because this delta Tm is 20 provided, right? And you can equate it to this Th in minus Tc out, right? This is Th in minus Tc out, which can be equated to this 20 degree, right? So Th in is given as 100, so Tc out can be 80 degree.
Sir, why x tends to 1 is the reason? What is the reason behind it?
I mean, as both are equal, na? Delta T1 and delta T2. Then only it will go to 0, and then only we have to apply the L'Hospital rule, right?
Sir, why they are equal?
Here here we have derived this, right? This is what we have derived, right? Delta T1 is equal to delta T2. right?
Okay.
Uh,
Okay, sir.
I guess you can skip this because as you have already derived this, right? This delta T1 is equal to delta T2. You can skip this also, right? From this only you can directly get this ET. Yes or no? Yes or no?
Yes, sir.
Yes.
Yeah. So if we go to the next one, in a parallel flow heat exchanger operating under steady state, the heat capacity rates of the hot and cold fluid are equal. The hot fluid flowing at 1 kg per second with this 4 kilojoule per kg K and enters the heat exchanger at 102 degrees centigrade, while the cold fluid has an inlet temperature of 15 degrees centigrade. The overall heat transfer coefficient for the heat exchanger is estimated to be 1 kilowatt per meter square Kelvin, and the corresponding heat transfer surface area is 5 meter square. Neglect heat transfer between the heat exchanger and the ambient. The heat exchanger is characterized by this following relation, right? Effectiveness relation is given. The exit temperature of the cold fluid you need to calculate. Can you try this one?
Yes, sir.
Yeah, so please try. Here this is parallel flow heat exchanger, right? So you will have this hot fluid and cold fluid, right? And you can have this THITCI, THE, right? You are given THI and TCI as 102 degrees centigrade and 15 degree, right? And MH is given as 1 kg per second, while the CPH is given as 4 kilojoule per kg Kelvin. U and A are also given, right? U is given as 1 kilowatt per meter square, sorry, 1 kilowatt per meter square Kelvin. Area is given as 5 meter square, right? So from this what they have given is same heat capacity is given, right? So here you will have MHCPH is equal to MCCPC is equal to 1 into 4 is equal to 4, right? Kilojoule per SK, right? Because kg will be cancelled when you multiply this. So now you are already given the expression of effectiveness, right?
B, sir.
Sorry?
B. B.
Yeah, let us see but how you can reach to that, right? So this you have this capacity as 4 kilojoule per second Kelvin. So basically whatever is given for your effectiveness, that is 1 minus exponential minus 2 NTU divided by 2. What you can do is you can calculate NTU first. NTU is what? Anyone remembers?
UAS by C minimum.
UAS by C minimum. So U and A are given as 1 and 5. C minimum is 4, which we already calculated. So NTU is 1.25. So if you put that into the above equation, then your effectiveness will be, can anyone tell what will be the effectiveness? Hello? Hello?
Yes, sir.
Sorry? What will be the effectiveness?
0.918.
0.46. Is anyone
Ah,
getting this 0.46?
yes, sir.
Huh? Anyone? Is anyone getting this 0.46?
Yes, sir. 0.458.
Okay, so once you get this effectiveness, then what you have to do is you have to calculate actual heat transfer, right? This actual heat transfer, which can be available from this effectiveness into Qmax, as we have already seen. But now you have calculated effectiveness and you have to calculate this C mean. Delta T max is Th in minus Tc in, as we know. So what is C mean, you know. What is Th in minus Tc in, that also you know. That is 102 and 15. So what is this Q max?
348.
348 kilowatt. So once you have Q max and effectiveness, you can calculate Q actual. So what is Q actual?
160.08.
160 kilowatt, right? So if once you have this, then you can equate it to this Tc out minus Tc in. Tc in given as 15. So 4 is also in the terms of that kilojoule, right? So that will be cancelled. 10 raised to 3 will be cancelled. So this 160 by 4 will be equal to Tc out minus 50. So now you can have your answer of Tc out.
55.02.
55, right? Almost. Yes or no?
Yes, sir.
So this is how you can have your Tc out as 55, right? Now if you go to the next one, then here water at 80 degrees centigrade enters the counterflow heat exchanger with a mass flow rate of this. Air enters at 30 degrees centigrade with a mass flow rate of this. If the effectiveness of the heat exchanger is 0.8, can you calculate this? Hello?
Yes, sir.
Sorry? Hello?
Yes, sir.
Please calculate.
Ma'am.
It is counter flow, right? So here you can use this effectiveness is equal to this actual heat transfer upon maximum heat transfer, because you are provided with this effectiveness as 0.8. If you consider first hot fluid, then let us say mH Cph is Th minus Th out upon this C mean Th in minus Tc in. So for C mean you need to first calculate both mH Cph equal to and mC Cpc equal to. So both are coming same, right? Because for hot fluid it is 2.09 into 1. Sorry, it is for cold fluid, right? 2.09 into 1, because for air, right, it is C is 1 and this flow rate is 2.09. So for cold fluid it is 2.09. For hot fluid, this flow rate is 0.5 and that CPH is 4.18. So here it is 2.09. So both are same, right? So C mean will be 2.09. Effectiveness is given as 0.8. Here this MH into CPH is 2.09. So ultimately this will be cancelled actually.
Is it 10?
Yes, correct. Right, so first if you calculate, then here in this case what you will get is this TH in is provided as 80, TH out you don't know, TH in and TC in both are provided as 80 and 30. So from this your TH out is equal to what will be TH out? 40 degree, yeah, right?
Yes, sir.
Similarly, as you have used this hot fluids heat transfer, you can consider cold fluids heat transfer, right, in effectiveness. That is TC out minus TC in. I am direct writing now because CC and that C mean are same. TH in minus TC in. So again this 0.8 into 15 into 14, then TC out is not given, right? TC in is given. So TC out will be 70. Yes or no? Hello?
Yes, sir.
Yeah, so in this case that LMTD is 10, but that temperature drop in particular is not equal to that 10, as somebody has asked previously, right?
Sir, it is straight line.
Yeah, almost, because this will remain same, right? Delta T will remain same. So you can consider, as I have told at that time also, this basically what we are discussing about is this delta T, which is it is going to remain same. So it does not necessarily mean that the same temperature is going to drop in both the liquid. Now it is clear, I guess.
मीन्स ऐसा हो भी सकता है या नहीं भी.
हाँ, that was coincidence that the same was drop as this LMTD, right?
And whenever CH and C are equal, then we are getting straight line.
Yeah. Here also it is same, right? That CC equal to CH, right? Here also.
Yes.
Okay then. So let us. This 10 degree is your answer, right? This one. Correct? So let us go to the next one. Yeah, in a concentric counterflow heat exchanger, water flows through inner tube at 25 degree and leaves at 42 degree centigrade. Oil enters at 100 degree centigrade and flows in annular flow passage. Exit temperature of the engine oil is 50 degree centigrade. Mass flow rate of water and engine oils are 1.5 kg per second and 1 kg per second respectively. Now the specific heat of water and oil are 4178 joule per kg K and 2130 joule per kg K respectively. Now the effectiveness of this heat exchanger is, you can calculate this, right? It is easy only. So can you try this one?
Yes, sir.
You know, right, this is equal to Q upon Q max. Here you can first check if Cc and Ch are equal or not. For water and engine oil, water is 1.5, Cph is 4, and 2130 for water. No, 4178 for water, sorry. Here 112. One and two. This 2130. So I guess C mean is this one, right? Where it is not Cc equal to Ch.
Sir, is the answer 2 by 3?
Yeah, correct. Here your Ch is C mean, right? So if you are having Ch as your C mean, then shortcut is you can have this Ch Th in minus Th out upon this C mean Th in minus Tc in. I guess you can use this, yes or no?
Ji, sir.
Yeah. So Th in and Th out are given as 150, right? And Th in is 100 and Tc in is 25. Correct? So this will give you 50 by 75, so 2 by 3. So 0.6667, right? 6667. This way you will get. Is it correct?
Yes, sir.
So everyone is getting this?
Yes, sir.
Now if we go to the next one, the saturated vapor is condensed to saturated liquid in a condenser. The heat capacity ratio is this. The effectiveness in condenser. Can anyone tell?
D.
D, sir.
Yes, correct. As we have already seen, right? This will be D. So now, if we go to the next one, then saturated steam at 100 degrees centigrade condenses on the outside of a tube. Now, cooled fluid enters the tube at 20 degree and exits at 50 degree. The value of lmtd. So can anyone tell? It's simple only, right?
$63.83.
Sorry,
63, sir.
63.82. Yeah, right, it is correct. So basically what happens here is this for saturated liquid it will remain this 100 degrees centigrade, while for cooled fluid it will increase. Actually this much, right? It is 20 to 50. So we can say this, let us say 20 to 50. So for this you need to calculate lmtd, that is delta T1 is 80, delta T2 is 50, and 11.55. Correct? This way only you can get your answer, right?
Yes, sir.
Yes.
This is 63.82. Okay. So here let us go to the next question. Here, during open heart surgery, patient's blood is cooled down to 25 degrees from 37 degrees using a concentric tube counter flow heat exchanger. Water enters to heat exchanger at 4 degree and leaves at 18 degree. Blood flow rate during the surgery is 5 liter per minute. Use the following data. Now effectiveness of the heat exchanger. Can you try this one? So first you can apply that energy balance, right? CH TH in minus TH out is equal to that CC TC out minus TC in.
0.4242.
Correct. So from this basically what you will get is the CH 37 minus 25 is equal to CC 18 minus 4. So CH into 12 is equal to CC into 14. So this says that this CC is C minimum, right? Because here CH is greater than CC. So CC equals C mean. So once you know this, then you can apply that effectiveness equation. Once you know this, then you can apply effectiveness equation. This is CC TC out minus TC in upon the C mean TH in minus TH out, right? So this will give E equals TC out, you know, right? 18 minus 4. Here you know 37 TH in minus TH. Sorry, here it will be TC in, right? For maximum temperature difference, it is TH in minus TC in. So that is why it is 4 again. So 14 by 33. This is 0.4242, right? Correct?
Yes, sir.
So your answer will be 0.42, you can write. So next is saturated vapor at 200 degrees centigrade condenses to saturated liquid at the rate of 150 kg per second on the shell side of a heat exchanger, right, where enthalpy of condensation is HFG is equal to 2400 kilojoule per kg. A fluid with Cp is equal to 4 kilojoule per kg Kelvin enters at 100 degrees centigrade on the tube side. If the effectiveness of the heat exchanger is 0.9, then the mass flow rate of the fluid in the tube side is. You can calculate this, right? Hello. Here you are having condensation, right? So condensing steam is at 200 degrees centigrade, right? So condensing steam is at 200 degrees centigrade, and this cold fluid is entering at 100 degrees centigrade, right? Okay. So what we need to calculate is we need to calculate the mass flow rate of the fluid in the tube, right, which is cold fluid, right, because steam will be around that cold fluid. So here your this C is 0, right, as we have discussed that C is 0. because C is nothing but this C mean upon C max. Here C max is infinite, so your C is 0, right? So for that your this effectiveness can be represented as the cold fluids this temperature, right? Because cold fluid Cc will be anyway C mean, right?
Sir, is the answer 1000?
Sorry,
Is the answer 1000?
correct. So here it is Th in minus Tc in. So effectiveness is given as 0.9. So here 0.9. Cc and C mean is same, right? Now Tc out you don't know. Tc in is 100. Th in is 200. Tc in is 100. This will give you Tc out equals to 190 degrees centigrade, right? So now once you have this, then you can go for heat balance. So heat balance in this case is that this mass flow rate of condensing steam into that enthalpy of vaporization, right, as we have discussed, right? And here you will have mc cpc into tc out minus tc in. So this for condensing steam, I guess it is given mass flow rate as 150 kg per second. 150 kg per second. HFG is given as 2400. MC you have to calculate. CPC is given as 4. Right, let us
90.
check this HFG and CPC. Right, here HFG is given as 2400, CPC is 4 kg per kg. So both are in this kg, right? So it will be cancelled, that turns to 3. And this TC out
90.
you have calculate 190, TC in is 100. Yes. So if you solve this one, then your MC will be equal to 1000, huh? Correct?
Yes, sir.
Kg per second. So you can write your answer here as 1000 kg per second.